All right, so first off, a couple questions from homework from last night, specifically number 93, which is the function f of x equals x cubed plus x squared minus 12x. All right, now you're asked to analyze the function, which more or less means, find all of your zeros, find your y-intercept, find your mins and maxes. In this case, in all cases, mins and maxes will have to be used, or will have to be found using the calculator. But everything else, hopefully, should be able to be found in this case without the calculator. So the first thing we might want to find are the zeros. So we're going to take our function x cubed plus x squared minus 12x and set it equal to 0 to find our x-intercepts. If we start off by taking out the GCF of x, right, we find that what's left over there is factorable. And it'll factor out into x plus 4 times x minus 3, right? And so we have 3 zeros at negative 4, 0, and positive 3. So there's 3 x-intercepts. Those can be found without the calculator. The y-intercept, f of 0 is just equal to 0 in this case, so it goes for the origin. Maxes and mins, we're going to have to go ahead and find graphically. We'll do that in a second, but first let's start to sketch out our basic idea of the graph here. Oh, max turning points because it's a cubic function. How many?
2.
It's always one less than the highest power. It's 2, so it can't have more than 2 turns in it, and it's going to cross at negative 4, 0, and 3. And 0 is also the y-intercept, of course, which makes sense. If it crosses the x-axis at 3, then that's also the y-intercept. At 0, sorry, and that's also the y-intercept. We also know that it's a cubic function, so its end behavior is going to be similar to that of x cubed. So the end behavior is going to be similar to the function x cubed because that's its highest term. And so that means it's sort of going to have to go off in that direction and then off in that direction as x gets very large, right? As x gets really large negative, it has to go to negative infinity. As x gets really large positive, it has to go to positive infinity. So knowing that, I would say that it's likely that this function looks something like this. If it has to come from those 2 directions and it has to cross those 3 and it can have no more than 2 turns in it, that's probably the best way to look at it, right? And so now the last thing we want to do is we want to find the maximum, the maxes and mins, right? The maximum right here and the minimum right here. We're going to have to use our calculator for that, so we'll go ahead and do that now. So if we use the max function in our calculator, when we find this one, we should get this is located at the point negative 2.36, 20.7. Right. And then the minimum here we'll also locate with the calculator. And the minimum will be at 1.69. Negative 12.59. And there we go. So located the maxes, the mins. We've drawn a rough sketch. Just by looking at the graph in the calculator, I confirm that that sketch that I drew, this rough sketch of the graph, is mostly correct. Or is pretty much entirely correct, so make sure that your assumptions you made about the graph were correct. The domain and the range in this case, because it's a cubic function, are both going to be all real numbers, right? So domain and range are both going to be negative infinity to infinity. And so those are all the things that you want to touch on if you're asked to analyze the graph of a function, right? Find all the important points like the x-intercepts, the y-intercepts, any maxes or mins, end behavior, how many turning points are there, domain and range. Those are all the things you want to be able to answer about a polynomial function when you're asked to analyze it. Okay? All right, so we're going to come back to polynomial functions in a little bit, but today we're going to actually start talking about rational functions, which are actually built from polynomial functions anyhow, so they are related very closely to polynomial functions. And a rational function is any function, whoops, of the form, say a rational function is r of x, of the form p of x over q of x, so it's a quotient of two other functions if p of x and q of x are polynomial functions. All right. So essentially what we're saying is that a rational function is just a quotient of two polynomial functions. Take two polynomial functions, divide them by each other, bam, there's your rational function. All right, and so the first fundamental question we're going to ask about rational functions are domain and range. Or let's not worry about range quite yet. Let's just look at domain of a rational function. So, for instance, if I had the function f of x equals 3x squared plus 2 over x minus 1. First of all, that's a rational function, right? Because it fits the definition of a rational function as the quotient of two polynomial functions. Once again, take two polynomial functions, divide them by each other, you got yourself a rational function. Now the domain, going back to what we talked about earlier about domain, are just all the possible values of x, right, that will give me real number values for the range. So what we're looking for are things that are going to make, that we usually find the domain of a function by identifying what's not in the domain, values of x that are going to give us non-real values for y. So how could we look at that, or how could we figure that out from this function right here? Can we see situations where we're going to get non-real values for y for certain values of x? Yeah, 1's not going to work. It's going to do what?
0.
Yeah, it's going to make the denominator 0. So x equals 1 can't be in the domain, right? X cannot equal 1. And so the way that I'd like to write what my domain is going to be, and that's the only restriction, right? There's nothing else that's going to cause this to not be a real number, right? If I plug in 1, I get a divide by 0 error, but that's about it, right? And so my domain then will be negative infinity to 1, union 1 to infinity, if I want to write it in interval notation. Okay. Now, in this case, because the denominator is so simple, it's really easy to see what's going to make the denominator 0, which is what we're looking for here. But in other cases, that's not necessarily going to be the case. And by that, I mean we might have to do some factoring, right? So what if I have the function x plus 2 all over x squared plus 2x minus 15. So in this case, and we'll call this function f of x as well, right? We have a function x plus 2 over x squared plus 2x minus 15, and we want to know what is the domain of this function. So we can't just necessarily tell readily by looking at the denominator what values of x are going to make that 0. So what we can do is do what? Okay, yeah, go ahead and factor the denominator here. So it's going to factor out to x plus 5 times x minus 3. And so 5 and 3 cannot be in the domain. So I could say the domain is the set. I'm going to use set builder notation for this one. Set of x such that x is not equal to negative 5 is one thing, right? It's going to make it 0. And x is not equal to 3. Right. So my domain is the set of all x such that x is not equal to negative 5 or x is not equal to 3. Okay. So domain, pretty basic idea here. Let's look at some really basic sort of functions now. Those ones would be the functions y is equal to 1 over x and the function y is equal to 1 over x squared. So these, first of all, also fit the definitions of rational functions. They're a quotient of two polynomial functions. And yes, 1 by itself is technically a polynomial. And so we can take a look at what their graphs look like. 1 over x, first of all, looking at 1 over x here, let's imagine that we just didn't know anything about 1 over x and we were like analyzing it entirely from scratch. First of all, what's the domain? Yes, x cannot equal 0. So there's something, if we look at the graph of this function, there's going to be something going on at 0. Right? But there's not going to be a value of y at 0. So this is going to be a what type of function? Is this going to be continuous or discontinuous? This is not going to be a continuous function because we have a value for y that is or the value of x where there's no y value that is that corresponds to that. What about symmetry? Is it an odd or even function? How can we tell? What do we think? I'm going to call this function f of x, and this will be the function g of x because I'm going to need that. So how do we figure out if a function is odd or even? Do you remember? So a function is odd if f of negative x, in this case, equals 1 over negative x, right? And that's the opposite of f of x, right? So if f of negative x is the opposite of f of x, then we know the function is odd, and it has symmetry about the origin, right? Now, like I said before, let's sort of, so we sort of know what's going on there. Let's, for a second here, take a look at what's happening at 0. So what's happening as x gets closer and closer to 0? We know at x equals 0, it's discontinuous. But what's happening as x gets closer and closer to 0? So we'll say the behavior as x goes to 0. Or gets closer and closer to 0, which a formal way of saying that is what is the limit? So we're introducing this idea of a limit now, which we say lim, as x goes to 0 of the function f of x. Right? It equals what? What's happening? As I put in smaller and smaller values of x, what's happening to the value of y? It's getting bigger and bigger and bigger. So if eventually, what are we going to get to? Do we think of it? It's blowing up really quickly. Yeah, it's going to go off to infinity, it turns out. So as x goes to 0, it approaches infinity. Right? And it turns out it really depends on which side you approach it from, because what happens if I plug in really small negative numbers? It's really big negatively, right? So it goes to what? So as I approach from the right side, from the positive side, if I plug in really small positive numbers, so I'm going to put a little plus here to indicate that I'm approaching from the right side, I go to positive infinity. On the other hand, if I approach from the other side, the negative side, if I put in really small negative numbers as I get closer, I put negative numbers in that are really, really close to 0, I'm going to approach negative infinity, right? So I'm going to just wait on x. Sorry. We'll get to that in a second. Is this thing already? No, it's not. Okay. And so the question is, okay, what is this graph? Nope. What is this graph then going to look like? Okay, so if I go ahead and draw my coordinate grid. So as we get really, really close to 0 from the left, right, what happens to the function is it just sort of blows up and gets really, really big, but in a negative way, right? And if we approach from the right, it gets really, really big, but in the other way. And then as x gets really, really large, what's going to happen? As x gets bigger and bigger and bigger, we're approaching what? 0, right? Because if I divide by a larger and larger number, it makes that smaller and smaller and smaller. Eventually, it's going to get to 0, right? And the same thing's going to happen from this side. And so that's why we end up having this sort of what we call a hyperbola. That's your basic hyperbola. And that's the graph of the function y is equal to 1 over x. And so that gives you a general sense of what that function looks like. Now, the question becomes a similar function, g of x. What if it's 1 over x squared? What if the multiplicity of that root on the bottom is 2 instead of 1? How is that going to affect what the graph looks like? Well, some of the basic stuff's going to be the same, like the domain, for instance, is still going to be x cannot equal 0. So we know the weird stuff is still happening at 0, right? What about the symmetry, though? Oh, and going back, well, we won't go back, but we saw before the symmetry of 1 over x was that it was an odd function, and so it was symmetrical about the origin, which the graph was, right? Now let's go ahead and make the same investigation here. What's g of negative x going to be equal to in this case? That's going to give us 1 over x squared. Yeah, it's going to be equal to g of x. So that means this is what type of function? And so it's symmetrical about the y-axis. Okay. So if our graph isn't symmetrical about the y-axis that we come up with, then we know we have some issues here. Now, let's get into the whole idea of what's happening as we get really close to the place where it's not defined here at x equals 0. What's going on here? And so what happens if I take the limit as x goes to 0 from the right side? If I plug in really, really small positive numbers, what's going to happen to g of x? It's going to get really big to, positive infinity, yeah. Now, on the other hand, what happens if I approach from the negative side? If I plug really, really small negative numbers into x squared?
It's still going to go up to infinity.
Which one? Positive or negative infinity? Positive, because it's x squared, right? So if I plug in really small negative numbers, it's going to get negative. In fact, this function can never be negative because x squared can never be negative, right? So that means it's going to also go to positive infinity. So it's going to look, this function is going to look a little bit different, right, than the other one. Right, and so it's going to go up to positive infinity from the left and up to positive infinity from the right, and it's also going to go off to 0 on both sides. So we can see this function is symmetrical, right? As we predicted, it is symmetrical about the y-axis, right? And it still has what we're going to start calling in a little bit here, a place where it sort of just takes off to infinity, a value for x where it takes off to infinity, we're going to call this a vertical asymptote. And with 1 over x, right, we also had a vertical asymptote. They look a little different because in one case they both go off to the same infinity, positive infinity, and the other one they sort of go off to different infinities, but nevertheless they are still still the same essentially. All right, I'm going to have you go ahead and graph, using transformations, and I want you to go ahead and graph a transformation of this function here. Go ahead and graph the function f of x equals 1 over x minus 2 squared plus 3. Well, let's do minus 3. Right? So this is just a transformation of the parent function, right? Y equals 1 over x squared. So do you know what the graph of 1 over x squared looks like? Use that to inform you as to how to graph that function using transformations. So what type of transformation do we have to do to the original parent function here? Yep, to the right 2 and then down 3. So if we're going to the right 2, our vertical asymptote used to be at 0. It's now going to be at 2, right? So what I'm going to do is I'm going to draw a nice dotted line for our vertical asymptote here. Whoops. Eventually. Oh, yeah. Wrong side. So it actually should be to the right too, not to the left too. All right, and so it's going to go up, and then it's going to go down by 3. So before it approached 0 as it goes off to infinity and positive infinity, now it's going to approach negative 3. So I'm going to go ahead and make a horizontal line at negative 3 here to remind myself what it's going to be approaching. And so the new function, doesn't really look horizontal, does it? Actually, I'll look at this. Will look something like that. And so it's going to go off to positive infinity here. And do sort of the same thing over here. Right, so it'll look something like that. Just shifted over to the right 2 and down by 3. All right. So that's your basic transformation of a rational function. We're also going to look at vertical and horizontal asymptotes. Let's first of all talk about a vertical asymptote. Whoops. A vertical asymptote occurs if the limit as x goes to some number c of some function f of x equals infinity. Essentially, right, as we get really close to some value for xc, it just shoots off to infinity. That's a vertical asymptote. And it can be infinity or it can be negative infinity, right? Right, and so what vertical asymptotes look like, and so it's sort of, we'll see here in a bit. And so the graph of a function can never actually hit that value, right? But what a vertical asymptote can look like, there's a couple of possibilities. We've seen both of them already, actually. So normally, like I said, we draw a vertical line for them. Sometimes vertical asymptotes look like this. One side will shoot up to positive infinity, the other one will go down to negative infinity, right? Other times with our vertical asymptotes, right, they might be both going in the same direction, right? They might both go up to they might both go off to. So vertical asymptotes occur at values of x that makes the denominator of the function equal to 0. As we saw with 1 over x and 1 over x squared, that's what happened there. That's what happens in general. And so if you have the function r of x equals p of x over q of x, if q of x equals 0, then we have a vertical asymptote, and so we want to find all the values of x that are going to make q of x equal 0, and those are all the places where we have vertical asymptotes in our function. So, having said that, functions and trying to find some vertical asymptotes here. So, for instance, I want you to go ahead and find the vertical asymptotes of the following functions. So, let's just say. So for the following functions, find the vertical asymptotes. The function r of x equals x over x squared minus 4. And r of x equals x squared minus 9 over x squared plus 4x minus 21. Go ahead and try and find all of the vertical asymptotes of those two functions by identifying all of the values of x that are going to make the denominator equal to 0. First function, how does that factor out? What do we think? How does that factor, the denominator?
X minus 2 and x plus 2.
Yep. Whoops. Try to see. Yeah, so x minus 2, x plus 2. So the vertical asymptotes are going to be at where?
2 and negative 2.
X equals 2 and x equals negative 2. Yep. And in a second, we'll go ahead and graph that and just confirm that that actually is the case. Now, this next one here is a little bit more interesting. So I'm actually going to go ahead and factor the top and the bottom. So there's the top, x minus 3x plus 3, right? And the bottom's going to factor out to x minus 3 times x plus 7, right? Now, you'd be tempted to go ahead and say, well, there's vertical asymptotes at x equals 3 and x equals negative 7. The issue, though, is that the x minus 3's cancel out, right? Leaving us with x plus 3 over x plus 7. So, it turns out that at x minus 3, there is going to be a discontinuity, but it's not going to be a vertical asymptote because the x minus 3 on top cancels out the x minus 3 on bottom. When they cancel like this, then that's not going to make this function. What's going to happen is instead of making this function approach infinity as we get really close to x equals 3, it's just going to approach x equals 3 nice and normally, no issues, no issues, no issues. And all of a sudden, when it gets to x equals 3, it just will be undefined at that very point, and that's the only point that it'll be undefined. So anytime they cancel like that, instead of being a vertical asymptote, it's just going to be a what we call a point discontinuity. So that function is a point discontinuity at x equals 3. So it's just not defined at that specific point, but it doesn't blow up to infinity at that point, which we'll be able to see on the graph in a second here. And it's going to have a vertical asymptote, but the one that doesn't cancel, which is x equals negative 7, right? All right, so let's go ahead and graph both of those to see if we were right about that. So for the first one, if we go ahead and graph it in our calculator, we get this graph right here, which we see that we do have the two vertical asymptotes we predicted at 2 and negative 2, right? This one goes down to negative infinity, this one goes to positive infinity, so that sort of matches what we predicted with our vertical asymptotes here. For this function right here, so for this last function here, as predicted, we only have a vertical asymptote at x equals negative 7. There is no vertical asymptote at x equals 3. So it just turns out what's going to happen there is instead of having that asymptote, there's just going to be a hole there. Right, so if we just make an open dot for that to represent the fact that at 3 it's undefined, but everywhere up to and approaching 3 it is defined, there's no vertical asymptote there. Okay, so that's vertical asymptotes and point discontinuities. We're trying to, those sort of, the big theme here is these all depend on the denominator of the function where it equals 0, and that's how we can tell about vertical asymptotes. So the big takeaway is denominator of the function, the behavior of the denominator of the function determines where we have vertical asymptotes. Okay? So now let's take a second to talk about horizontal asymptotes. All right, so horizontal asymptotes, let's start off with the graphs. We've seen a couple examples of them so far. We haven't necessarily called them horizontal asymptotes. But in the graph of y is equal to x, we see that, right, we never really crossed the line y is equal to 0 here, right? Because as x goes out to infinity, it's just going to get closer and closer to 0 without ever quite getting there. And the same thing's true as we go to negative infinity here. It's going to get closer and closer to 0 without quite getting there. And you could have other examples of functions where maybe the horizontal asymptote is not 0. Maybe it's something else. So, like for instance, this function right here. It helps to start with a horizontal line. So, as I was saying, let's say maybe we have a function that approaches that line as we go out to infinity. That would also be an example of a horizontal asymptote. So, anytime we have a function that as we go out to either positive infinity or negative infinity, it gets really close to it, it sort of approaches a line without quite getting there, we are going to call that a horizontal asymptote of a function. So what's happening here, let's say this function is f of x. We'll call this function f of x. I just talked about limits a second ago. What's happening here is the limit as x gets really big. So let's look at this side. As x gets really big here, the y value is eventually it's getting close to 0, but never quite getting there. But the limit, let's say if we went all the way out to positive infinity of f of x here would be 0, right? So we'd say that's 0. So then the line, if that's the case, then the line y equals 0 is a horizontal asymptote. Right, and on the other hand, as x goes to negative infinity, that's also the case. So the line, same thing's true. The line y is equal to 0 is a horizontal asymptote of the function. Let's say for this function that this is the value 3 here, and this is the function g of x. Then we'd say here the limit as x goes to infinity, the limit as x goes to infinity of g of x is going to equal 3. Right? It's getting closer and closer to 3 without never quite getting there. And so the horizontal asymptote itself is the line y is equal to 3. That's the horizontal line that it never crosses, right? Right? So the question is, if we just look at the, if we look at a rational function, how can we tell if that rational function is going to have a horizontal asymptote just by looking at the formula of the function without having to graph it on a graphing calculator, which, as always, is what we're trying to strive for here. It turns out, and you can sort of think about this, if we have some rational function, so for any rational function r of x that equals p of x over q of x, right? think about this. If p of x increases faster than q of x, what do you think is going to happen as we go to infinity? If the numerator were to be increasing faster than the numerator is outgrowing the denominator, what's going to happen to that value of that p of x over q of x?
Make it bigger.
It's going to keep getting bigger. So it's just going to go off to infinity, right? What if, on the other hand, what if q of x gets bigger faster?
It's small.
It's going to get smaller and smaller and smaller until it eventually gets to
Oh. Negative
0, right? Yeah.
Oh.
So if q of x is going to increases faster, then it's going to go to 0. If p of x increases faster, it's going to go to infinity. And if it turns out if they increase about the same rate, then it's also then it's going to go to some constant value. So, and with the rational function, which functions do you think increase faster than which other ones? Do you think higher order functions increase faster than lower order functions? Like an x to the fourth, would that increase faster than x squared? Yeah. So you're looking for the order of the function. So in general, so in the first scenario, we talked about 3 separate scenarios here. If q of x is a higher order polynomial than p of x, right, then first of all, then r of x is a proper rational function. That comes from the idea of a proper fraction, where the denominator is larger than the numerator in a proper fraction. So if you have a proper rational function, that means the denominator is a higher order than the numerator. So it's proper, and that means that the limit as x goes to infinity of r of x has to be 0, because the denominator, is increasing faster than the numerator. And when the denominator increases faster than the numerator, we're eventually going to get to 0, right? As x gets really, really, really big. And y equals 0 is the horizontal asymptote. So if the function has a horizontal asymptote of y is equal to 0, that's really easy to tell, because any function where the denominator has a higher order than the numerator, immediately you know y equals 0 has to be a horizontal asymptote. If q of x, whoops, not g. On the other hand, if q of x is the same order as, actually, let's look at an example of that first before we go into the other possibilities. So this first scenario is if p of x and q of x, if q of x is a higher order. So for example, if we have the function f of x equals x minus 12 over 4x squared plus x plus 1. Right, there's a rational function. Now, do we see that the bottom is a higher order than the top? It's a quadratic and the top is a linear function. So the quadratic's always going to increase faster. It's going to get bigger faster than the linear function as x gets really big. So right away we know that y equals 0 must be a horizontal asymptote. And if we go ahead and graph that function, so if we go ahead and graph that function, f of x, on our graphing calculator, we get the following graph, and that confirms that, yeah, y equals 0 is a horizontal asymptote, right? We are definitely, as we get out to the left here, we're approaching infinity, or approaching 0 as we go to negative infinity. We're approaching 0 as we go to positive infinity. So that's a relatively simple case when we have a situation like that. Now, on the other hand, if we have the following, if we have the function, the rational function, once again, r of x equals p of x over Q of x, and P of x and Q of x are the same order, like they're both quadratics or they're both cubics or something of that nature, then the limit as x goes to infinity of r of x is just going to be some number c, which we're going to determine based on the polynomial function. So it's going to have a horizontal asymptote for sure. It's just that that horizontal asymptote is not going to be 0. So where c is not equal to 0 in this case. So it's going to have a horizontal asymptote that's not 0, and the question is, how do we determine that? All right, well, let's look at an example here. Let's say I have the function r of x equals 8x squared minus x plus 2 over 4x squared minus 1. So first of all, this is an example of a function where the top and the bottom are of the same order, right? Now, it turns out that as x gets really, really big here, right, that this term, as x gets really, really big, the 8x squared term and the 4x squared term grows so much faster as x gets really, really large than both negative x and obviously the constant parts don't grow at all, right? But in any case, because this term grows so much faster and this term grows so much faster than the other stuff, like the negative x here and the 2 and the 1, that they grow and they completely dominate what this ends up being equal to. And so it turns out that these terms right here end up not really mattering in the grand scheme of things. Okay, they end up not mattering at all. And so what that means is as x gets very large, as it goes to infinity, r of x is roughly equal to 8x squared over 4x squared, right? It's going to be roughly equal to that because the lower order terms here don't really matter so much. The lowest order terms on the top and the lowest order terms on the bottom aren't really going to affect the value of r of x when x gets really, really big because, you know, think about, for instance, if I had like 2052 plus 1 over 3,784 plus 2. Are the plus 1 and the plus 2 really going to make that big of a difference in the decimal version of that number? Not really. And imagine that's going to even get smaller and smaller as those numbers get larger and larger, right? So that the same reasoning holds true for why these terms aren't going to matter as x gets really, really, really big. So when you have a situation where the top and the bottom are of the same order, right, you're going to go ahead and look at these terms and just say, well, they don't really matter, and so I'm only concerned with the highest order terms, right? So this was just an example to sort of show that point. In any case, so that's equal to what? Can I reduce that to something? What does that reduce to? 2. So as x gets really, really, really big, these are the only two terms that really matter, and because of the same order, they just reduce down to a nice constant value, which in this case is 2. Therefore, y equals 2 is the horizontal asymptote. Let's go ahead and confirm that with the graph of the function. So I meant to use the therefore thing here. Yeah, therefore. So if I go ahead and I graph the function r of x on my graphing calculator, I get this graph right here, which does indeed have a horizontal asymptote of 2. So we see that this is the case. So far, if the top and the bottom, if the bottom has a higher order than the top, then the horizontal asymptote is always 0. If the top and the bottom have the same order, then I take out just the highest order terms in the top and the bottom, and I reduce them down to whatever constant value I get to, and that's going to give me my horizontal asymptote. Now, the next scenario, of course, if we have the function r of x just as before, and p of x is higher order than q of x, right? Then, well, what's going to happen if the top of the function is increasing faster than the bottom? What do we think the function is going to end up getting to? It's going to go off to infinity. So we would say the limit as x goes to infinity of r of x in this case equals infinity. And if the y value is going off to infinity, do we have a horizontal asymptote?
No.
Then there is no horizontal asymptote. Right? However, that doesn't mean that we can't still sort of look at the end behavior. So there's no horizontal asymptote, but the question is, so the horizontal asymptote, that's a type of end behavior, just like we talked about with polynomial functions, right? And so we have other possible end behaviors. So for example, let's look at the function let's say 3x to the fourth minus x squared over x to the third minus x squared plus 1. So, in this case, the top is a higher order than the bottom, right? And so what we're going to have to do here is, in its improper form, we can't really get a good sense of what's general. We know that the limit for h of x here, our function h of x, we know the limit is infinity. As x goes to infinity, h of x goes to infinity, right? But we don't necessarily know how it gets there. How quickly does it get there? How does it behave once x gets really, really big? That's our question. We want to know what is the end behavior, right? What is the end behavior? Right? First of all, horizontal asymptote is a type of end behavior. So we've already talked, I mean, by finding the horizontal asymptotes, we found the end behavior of those other functions. But if a function doesn't have a horizontal asymptote, the question is, well, what is the end behavior then? If the end behavior isn't a horizontal asymptote, it can be other things, potentially. So to investigate that, we're going to have to do some polynomial long division here. So we're going to take this and we're going to break it apart by dividing the top by the bottom. So anytime we have an improper rational expression where the top is a higher order than the bottom, we want to go ahead and divide that out. So we're going to have to set up our polynomial long division here, which I'm going to actually do on the next page because there's not going to be enough room otherwise. So the function again was h of x, whoops, h of x equals 3x to the fourth minus x squared over x cubed minus x squared plus 1. So we got to go ahead and do some polynomial long division. So we're going to go ahead and set up, I need more room than that. We're going to set up our long division so we have, so we have 3x to the fourth minus x squared. Oh boy, that's being divided. We'll get there eventually. So, sorry, we have what's dividing is, or doing the dividing is x cubed minus x squared plus 1. And we're dividing out 3x to the fourth minus x squared. So when we have missing powers, like there's no cubic power here, there's no linear, and there's no constant power, we're going to go ahead and add in placeholders for those. So we'll say that we have 0x to the third, right, minus x squared plus 0x, right, plus 0 for the constant term. So we put in, just like we do with normal long division, we like to put in we like to put in placeholders when we're doing our polynomial long division so that it makes it easier and we don't forget things. All right, so the first thing we want to do is we have to ask ourselves, how do we make the first term of our, what do we call this? This is the divisor, right? The first term of our divisor, how do we put that into the dividend? What do we have to multiply x cubed by to make it into 3x to the fourth? 3x. Whoops. So yes, we have to multiply it by 3x. So x cubed times 3x is 3x to the fourth. And then we have to multiply the whole thing through that. So negative x squared times 3x is negative 3x cubed. And 1 times 3x. And notice I'm lining them up. So I'm going to take this 1 times 3x, and that's going to be positive 3x. I'm lining it up with the place that it's in. So I'm not putting the 3x underneath the x squared, or the negative x squared. I'm putting it under the 0x. Because when we go ahead now, we're going to go ahead and subtract this, right? Just like we do in long division, we're going to subtract whatever this is from whatever we have here. Right, so 3x to the fourth cancel. 0x cubed minus negative 3x cubed. Well, we're subtracting a negative, so we're really adding, right? The negative x squared just drops down because there's nothing to add or subtract to it. And then we're subtracting 3x, so we should get negative 3x, right? Plus 0 still. Right, and so that's the process we're just going to keep repeating all the way down. So now we have to ask ourselves, how does x cubed go into 3x cubed? We have to multiply it by what?
3.
Got to multiply it by 3. And so we'll get 3x cubed. And then negative x squared times 3x is negative 3x squared. And then plus 3. Right? And if we go ahead there and subtract, we get the negative x squared minus negative 3x squared. We're essentially adding 3x squared to negative x squared. So we're going to get 2x squared, drop down the negative 3x, and then the plus 3. Right? And we're just going to divide as long as we can until we get to the situation where, right, can x cubed be multiplied by any monomial to make it 2x squared at this point? No, so once we get to the point where the first term of our dividend can't go into the first term of what we have left over here, then we know at this point this is our remainder. Right? And in this case, if this is the remainder, and this is our quotient, right, just like with any long division, this is going to be equal to the quotient plus the remainder over the divisor. Whoops. Right, and to make you to sort of understand that better, like if we did, for instance, 5/4, right, is equal to the quotient. 5 divided by 4 is what? It's 1 plus 1 over 4, the remainder over the divisor. So it's the same exact idea with polynomial fractions and dividing. It's the quotient plus the remainder over the divisor. Whoops, sorry, that should be negative 3 actually. It's not really going to really mess anything up, but that should be, instead of positive 3, that should be negative 3. Let's fix that in the other one as well. So that should be negative 3. So, what this all means is if we go ahead and we look at this little situation right here, and I'm actually going to go ahead and, this is a nice little example here, but I'm going to go ahead and erase this now so that I have more room to work down here. What this all means is, if we take, knowing that h of x equals this right here, if we take the limit as x goes to infinity of h of x, right? Right, what's going to happen to this expression right here as x goes to infinity? The whole remainder over the divisor part. The remainder over the divisor is always going to be a proper rational fraction. The top is always going to be a lower order than the bottom, meaning what's going to happen to this fraction right here as x goes to infinity?
It's smaller.
Until it becomes
0.
So this is going to go off to 0. This is going to keep increasing though, right? So the limit as x goes to infinity of h of x is the same, really, as the limit as x goes to infinity of 3x plus 3, which is to say that they both go off to infinity. But now we know that sort of h of x, as it gets really big, this part doesn't matter anymore, and this part takes over. And so h of x behaves like 3x plus 3, right? It behaves a lot like 3x plus 3 as x goes to infinity. And so what we end up getting here is what we call an oblique asymptote. Anytime the end behavior is linear and it's not a horizontal line, we call it an oblique asymptote. Right? And how is that going to show up in the graph? We go ahead and we graph this function in our graphing calculator. Right? We're going to see that it's going to look like this function right here, right, as it gets really big. So I'm going to go ahead and just draw a dotted line for the linear function 3x plus 3. So 3x plus 3, we go up 3, and it's a slope of 3, so it's going to look, roughly like this. Right? And I'm claiming that as the function gets really big, it's going to look like that. So let's go ahead and graph it and see what happens. All right, so if we go ahead and we go ahead and graph it, it turns out the function sort of looks like this. So as we go to positive infinity over here, it approaches the line as we expected, and as it goes to negative infinity, it also approaches that line. It also, just for reference, has a vertical asymptote, which we could probably find too, but we're only really interested in this oblique asymptote right here. So this is an oblique. I wrote down there, but that's an oblique asymptote, right? So anytime we have an end behavior that's linear and it's not a horizontal line, if it's just a flat horizontal line, we call that a horizontal asymptote, and that would be the end behavior. If it's a linear function, that's the end behavior, then it's an oblique asymptote. And if it's anything else, then we just call it nothing. We just say that's the end behavior. So having just said that, why don't you guys go ahead in this next one, use the same process involving polynomial long division. The function g of x equals 2x to the 5th minus x cubed plus 2 all over x cubed plus 1. Figure out the end behavior of that function. So since we're running low on time here, I did it all out already, so here's your long division, your remainder's here, you end up getting this, and so your quotient is 2x squared minus 1. So that means that the limit as x goes to infinity of g of x looks a lot like the limit as x goes to infinity of 2x squared minus 1. And this function, 2x squared minus 1, which is a quadratic, is our end behavior model right here, or our end behavior. This is what the function behaves like as x gets really, really large. And if we go ahead and graph that, first of all, that function 2x squared minus 1, so the function 2x squared minus 1 sort of looks like this dotted line here. And then if we go ahead and graph our actual function here against that. So if we go ahead and graph that, we see that, yeah, once again, we sort of have this weird vertical asymptote right here. But as we go off to negative infinity, it sort of conforms to this curve right here, right? It goes off and it acts like this function, 2x squared plus 1, as x gets really big here, and as x gets really big to the left here. So that's the idea of end behavior. So this one is not an oblique asymptote, right, because it's not linear, it's a quadratic, and we don't really have a name for it. It's quadratic end behavior. That's all we really can get at there. But it is an end behavior, nonetheless. So to sum up, our end behaviors can be horizontal asymptotes, they can be oblique asymptotes, and they can just be anything else, depending on the order of the top and the order of the bottom of our rational function. All right, so the homework for tonight. So the homework for tonight is the following. It's from the new 4.1 handout, which I emailed out to everyone and I passed out in class today. Please let me know if you have any questions, and have a good day.